In this video, we're going to review chemical and physical changes, so how we can identify if a chemical change has occurred, and then we're going to introduce balancing chemical equations, and then types of chemical equations. So recall from earlier, a physical change, with a physical change, the chemical composition of the substance remains constant. So for example, water going from a liquid to a gas, we still have water before and after. It's just changing its physical state. It's changing from a liquid form to a gaseous form, but we still have water. So that's called a physical change. Another example, melting ice, boiling water. Another example we could do, dry ice. So CO2, if you buy it in the solid cold form from the grocery store, we call that dry ice, and it sublimes into gaseous CO2. That's another example of a physical change because it's still carbon dioxide before and after. Now, with a chemical change, the chemical composition of the substance is changing. So we might start off with like hydrogen gas and oxygen gas, and we make water molecules when we're done. So we have two different substances combining to make one new substance. That's an example of a chemical change because the chemical composition is changing. So during a chemical reaction, new substances are formed. So there's a few different things you can look for to try and identify if a chemical change has indeed happened. So we're going to go over 4 different observations that can indicate that a chemical reaction has taken place. So number 1, a gas is produced. So if you see bubbles, for example, gas may be observed in many different ways: light fizzing, heavy bubbling, just anything that indicates that you have bubbles. Here, their example, they've got magnesium with an acid. So for example, magnesium solid metal plus HCl. One of the products that we would make is H2 gas. We would make other products as well. But anytime you see a gas, you're making a new substance, so that's an example of a chemical change. If you make a solid, so an insoluble solid product, so here, this yellow stuff, that is a new substance being formed, and we see the color change, but what's happening here is it's the solid is forming and then it's precipitating out of solution, so we call it a precipitate, and then it eventually collects at the bottom of the container, and we could do further separation by spinning it in a centrifuge or filtering it if we wanted to actually collect that solid. But if you add 2 aqueous solutions together, sometimes you may observe solid product, and it may not always be a nice color. Many solid products are actually white, but the point is that's another example of a red flag that you have a chemical reaction actually occurring. Another one is a permanent color change. So this kind of same example, if you see something change, like you mix 2 white liquids, now suddenly you have some red appearing, or 2 colorless solutions and then some red stuff appeared, you have a color change, so that's telling you that a chemical reaction occurred. Another one is there's some sort of energy change, so energy being released or energy being absorbed. So if energy is released, we call it exothermic, and an exothermic reaction would feel hot. So if you had a reaction that occurred in a test tube and you actually held that test tube in your hands and the test tube felt hot or warm to you, that would be an exothermic reaction. Energy is leaving the reaction, which is going to be classified as the system, and it's going into the surroundings, which includes the test tube and your hand. Because there's an energy change, we know the chemical reaction must have occurred. And if the reaction absorbs energy, then we call it endothermic, and endothermic would feel cold. So you do the reaction in your test tube, you hold the test tube in your hands, and it feels cool or cold. That's an indication that a chemical reaction has occurred. Another one, like in the picture, sparks or fire. So if we add an alkali metal, so one of the metals from group 1 on the periodic table, those are extremely reactive with water. If you put those with water, you'll get sparks and even a flame or an explosion, depending on how much. Another example of a chemical reaction. So when we have chemical reactions, we express what happens using a chemical equation. So a chemical equation describes a chemical reaction using formulas and symbols. So this is just a general form of a chemical reaction. We say A plus B yields C plus D. So the arrow is showing, the arrow means yields, and we're kind of showing the before and the after with these chemical equations. The A and the B are known as reactants. So whatever's on the left side of the arrow, we call reactants. And whatever is on the right side of the arrow, we call products. We could also have a catalyst. So we could also add a catalyst to a reaction. A catalyst, if we had one, would be written above the arrow. And what catalysts do is they speed up the reaction without actually being consumed. So if we had a catalyst for this reaction, let's say the catalyst we're calling E, we would write it above the arrow like this. And catalysts, again, they speed up the reaction, but they're not actually consumed in the reaction. So they're used, but then they're regenerated later. When writing chemical equations, we usually specify the physical state of the reactants in the product. So that's referring to this part. So we're saying A in the gaseous state, and then B is a liquid, yields C, which is a solid, and it yields D, which is aqueous. So the AQ means aqueous, and aqueous means it's simply dissolved in water. So A is gaseous, B is liquid, C is solid, and D is aqueous, dissolved in water. So this is kind of a summary of the different symbols you could see. So again, here's your arrow. An arrow means yields, or basically produces. Anytime we have multiple reactants or products, we use a plus sign. We're never going to have minus signs. And when we talk about redox reactions later, you might be tempted to use a minus sign, but we never use minus signs in chemical reactions. Here's two examples of a catalyst. So we're writing the symbol above the arrow. So this little triangle is saying heat. So we're saying heat is a catalyst with the way that's written. And the second example, we have Fe for iron. They're saying iron is a catalyst. So it's just two examples of different catalysts and what it would look like if you had it in the reaction. If you have something where you know nothing actually occurs, and we can talk about examples of where that would show up, we'll use capital N, capital R to indicate no reaction. And then these are the physical states that we will often use. So solid, liquid, gaseous, and then aqueous. Again, aqueous to indicate that something is dissolved in water. So here's an example of a chemical reaction. And if we were to basically read this out like a sentence, it would be phrased like this. So we have aqueous acetic acid is added to solid sodium carbonate, and it yields aqueous sodium acetate and liquid water and gaseous carbon dioxide. So this is your sentence form, this is your symbolic form, both are expressing the same thing. Now, I've mentioned this before, but there are 7 diatomics that you need to memorize, and the reason why this is important is because if you were to have a chemical reaction expressed as a sentence, if for example we said hydrogen gas plus oxygen gas yields water, you need to know that hydrogen and oxygen are actually diatomic molecules. So it would be incorrect to say H plus O makes H2O. You'd have to know that it's actually H2 plus O2 makes H2O. And we haven't even talked about balancing yet, but these are the 7 diatomics. You may need to memorize them. And one way or one trick that I have for memorizing is there's 7 of them. And then here they are located on the periodic table. And that kind of looks like a 7. But wait, let's check. That's 1, 2, 3, 4, 5, 6. That's only 6 of them. Aha, here's number 7, the hydrogen. So that's just my trick on how to remember. But important, just these when they're naturally occurring, so when they're in nature by themselves, not chemically bonded with other elements, they occur as 2 atoms covalently bonded together. So that's why we're saying diatomic. Now, not all of them are gases. Many of them are, but this one's a gas. Hydrogen, nitrogen, oxygen, fluorine, chlorine, and then bromine at room temperature is actually a liquid, and iodine at room temperature is actually a solid. So then next thing, when we write a chemical reaction or chemical equation, it's really important that the number of atoms of each element must be the same on both sides of the arrow. So this is getting into balancing. So we're just talking about the essentials of chemical equations and what we mean, but then whenever you have a chemical equation, you need to make sure that it's balanced. And we're looking for basically conservation of mass, or in this case, the way they're talking about it on the slide, conservation of the number of atoms. So the number of atoms of each element needs to be the same. Now we balance chemical reactions by placing a whole number, and we call it a coefficient, in front of each substance. And a coefficient effectively multiplies all the subscripts in a formula. So with this example, they have 3H2O. This 3 is kind of like it's being multiplied across. So the 3H2 means there's 6 hydrogen atoms, and the 3 for the oxygen means there's 3 oxygen atoms. It would be incorrect if you wanted 3 water molecules. It would be incorrect to change H2O into, I don't really want to put an arrow, I don't want you to think it's a chemical reaction, but to write H6O3, that would be very, very incorrect. We don't want to do that. We only put whole numbers in front, and we call those coefficients to indicate if we need to have more atoms on either side. So before placing, and these are guidelines or tips for balancing. They say guidelines, I would call them more like just tips or recommendations, but before placing any coefficients, so before you even attempt to balance a chemical equation, double check that all the formulas are correct. So if we give you a chemical reaction as a sentence, and you have to write the formulas from the names, which we talked about in a previous video, make sure those formulas are actually correct before you begin, because if your formulas are incorrect, I guarantee that balancing will be near impossible. Next thing is never ever change the subscripts. So again, if you want 2 water molecules, you are not allowed to say H4O2. Don't do that. Never ever change the subscripts. One thing that they recommend, balance each element in the equation starting with the most complex formula. So by more complex, for example, the H2O versus C2H3O2. This one's more complex, so they're just recommending start with this one. And we can do examples in another video to kind of give you guys some practice. Another hint that you can do, it says balance polyatomic ions as a single unit if it appears on both sides. So for example, if we have NH4Cl plus, just making up an example off the top of my head, NaNO3, and then yields NH4NO3 plus NaCl. They're saying that these polyatomic ions, the ammonium and the nitrate, you just treat them as a single unit, almost like it's its own element for balancing. Another tip, the coefficients have to be whole numbers. So you're not allowed to have like 1/2 of a water molecule. It has to be 1 water molecule or 2 or 3 or 4. If you do get a fraction, or you feel like you need to use a fraction just to make it balanced, what you can do is then multiply the entire equation by the denominator to make them whole numbers. So here's an example where we're attempting to balance the hydrogen plus oxygen gas makes water. And we realize if only we used a 1/2 right here, then it can be balanced. Then to resolve the issue, to get a properly balanced chemical equation, they're just multiplying everything by 2 because our denominator here is by 2, so that you actually get whole numbers. Now here it's a 2, here it's a 2. For the oxygen, there's no number written in front because there's a 1 right there. So just as a general tip, anytime we have 1 for our coefficient, we usually don't write it in. Another thing, after balancing the equation, check, of course, that there are the same number of atoms of each element on both sides, because that is the entire point of balancing. So with this example, we see that we have 4 hydrogens on the right on the left and 4 hydrogens on the right. And with the oxygens, we've got 2 on the left. And then here we have 2 times the 1 in the formula. So there's 2 oxygens on the right. So we have 4 and 4 and 2 and 2. We have the same number of atoms for each element on both sides. So the equation is indeed balanced. Finally, check that you have the smallest whole number ratio for the coefficients. So for example, this one, we were given this chemical equation and they balanced and they got 2, 2, and 4. Notice that 2, 2, and 4 are all divisible by 2. So we can simplify our answer by just having 1, 1, and 2 for our coefficients. So that's what we mean by this smallest whole number ratio. If you can divide all the coefficients by some common factor, do that to get your final answer for a balanced chemical reaction. So here's an example that we're going to walk through where it says balance the following chemical equations. So we have this aluminum sulfate and then barium nitrate, aluminum nitrate, and barium sulfate. So one tip that we can do is, again, treat the polyatomic ions as single units. So here they're kind of walking through our thought process, but they notice that there's 1 sulfate on the right side, that's right here, and there's 3 on the left. So that's this part right here. We've got sulfate, and then there's 3 of them. So they're saying place a 3 in front of the barium sulfate. So we put a 3 right here. Next, they're noticing there are 2 aluminums on the left. So that's this part right here, and only 1 on the right. So there's only 1 aluminum right here. So they're saying maybe place a 2 in front of the aluminum nitrate. So we put a 2 right here. So this is what we have. This is the work we've done so far. Now there's 3 barium on the right. So after we've kind of initially worked, we notice now we have 3 barium on the right, but only 1 on the left. So maybe we put a 3 right here. And then here is what they're suggesting as our final answer. So we can just check it. We've got 3 barium and 3 barium. We've got 3 sulfate and 3 sulfate. We've got 2 aluminums and 2 aluminum. And then we've got 2 nitrate, or sorry, we've got 3 times 2 nitrates. So that means there's 6 nitrate. And then here there's 2 times 3 nitrate. So there's 6 nitrate. So we're just checking, making sure that we have the same number of atoms on each side and same number of polyatomic ions on each side. So next we're going to talk about classifying chemical reactions, and I've got 7 categories right here. We are not going to talk about all 7 of the categories in this video, but we'll eventually go through all of them. So combination, which is also known as a synthesis reaction, decomposition reactions, so something that's being broken up, single and double replacement, which may also be called single displacement reactions and double displacement, depending on where you're reading it. Neutralization reactions, which are also called acid-base reactions, oxidation reduction reactions, and then also combustion. Now these 7 categories are slightly different than what the book has. I think the book only lists 6 categories. I've expanded it to 7, but we'll go through all of these in due course, but not all of them in this video. So first one, a combination reaction, is a reaction in which simpler substances are combined to a more complex compound. So for example, A plus B makes C. So A and B have been combined into a single compound called C. That's what we mean by a combination reaction. They're also known as synthesis. So we're going to look at 3 different types of combination reactions, 3 specific examples. Anytime we have a metal with oxygen, it's usually a combination or synthesis reaction. If you have a nonmetal with oxygen, it can be a combination or synthesis. And then the reaction of a metal with a nonmetal. So first off, a metal with oxygen gas, what we're going to usually make is the oxide of that metal. So for example, magnesium metal, heat it up. So here's our symbol for heat with oxygen gas. We make magnesium oxide. So again, we have 2 things combining to make 1 thing. So that's why we're calling this a synthesis reaction, because we have 2 two reactants makes one product. And again, here's heat acting as our catalyst. So again, that's a new term. Make sure you're familiar with that. Catalyst, we write those above the reaction arrow. Next one, reactions of a nonmetal with oxygen. So very similar. So A plus B yields some new product. So we're making the oxide form of the nonmetal. So here's another example where you have sulfur plus oxygen gas. Again, we're using heat as a catalyst to make sulfur dioxide. So again, it's A plus B makes C. That's why we're going to classify this as a synthesis or combination reaction. And then next type of synthesis or combination reaction, a metal and a nonmetal. So A plus B yields some new substance C. And in this case, it's an ionic substance, but our example here, we've got lithium plus bromine gas. And I did say that bromine at room temperature is liquid, but here they're saying it's a gas. It doesn't necessarily have to be at room temperature, and it probably isn't because after all, we are using heat as a catalyst. So we've got bromine as a gas plus lithium as a metal, as a solid, makes lithium bromide. So again, it's A plus B yields some new substance C. So that's why we're going to classify this one as a combination. So then when a main group metal reacts with a nonmetal, the formula of the ionic compound is predictable. So this goes back to when we were talking about nomenclature. So like lithium, for example, that's in that first column. So you know that lithium as an ion is always going to be +1. And then bromine is a halogen, it's always going to be a -1. So when these two come together, it has to be lithium bromide where it's just one of each. That's what they mean by it's predictable. We can predict the formula just based on the charges. And then if the compound was a transition metal, then the formula would not be predictable. So we'd have to know what charge the metal is becoming, essentially. But that's what this bullet point is emphasizing. Okay, the next type of reaction that we're going to talk about this week, so decomposition, it's basically the opposite of what we were just talking about. So combination synthesis reactions, we're making a new substance from simpler substances. Decomposition is the opposite, where maybe it's C breaks down into A plus B. So a single compound is broken down into two or more simpler substances. And they're saying heat is usually required to start a decomposition reaction. So you heat something up and then it breaks up into smaller things. Example includes ionic compounds containing oxygen will often decompose into the metal and oxygen gas. So here we've got mercury oxide or mercury 2 oxide producing mercury metal. And note that it's a liquid. Mercury is one of those exceptions. It's a liquid at room temperature, producing mercury metal and oxygen gas. So something breaking up. And I'm using C, A, and B, but we could use any letters to represent these. But you have one substance breaking up into multiple simpler substances. So an example of this that we could do in the laboratory, carbonate decompositions. So this CO3, this is your carbonate, and this is actually hydrogen carbonate with the hydrogen in front, or it could be also called bicarbonate, but you've got this nickel bicarbonate, or they're calling it nickel 2 hydrogen carbonate, that's the same thing. And then we use heat to start the reaction, and then we're breaking it up into 3 compounds. So that's why we're going to classify this one as a decomposition reaction. Metal carbonates decompose to give the metal oxide and then carbon dioxide gas. So here's another example. Here's calcium carbonate. Here is the metal oxide. And here is carbon dioxide gas, but it's the same kind of thing. We've got one substance breaking down into simpler substances, so we call it a decomposition reaction.